Problem number 25. Well, once again, the difference of two squares, right? This is 81 is a perfect square, s squared is. 25 is a perfect square, so is p squared. So let's write our two sets of parentheses, anticipating we can do this in terms of our conjugate. So just undo each square. How about 9s, right? Because if we take 9s and square it, we'll get the 81. And then 5p and 5p. Make 1 plus, 1 minus, because it is the difference of two squares. So we know that we end up with this factored form, and these are conjugates. And if we multiply it out, these two middle terms are going to cancel, remember? So we'll get negative 45 ps and positive 45 ps. That goes to 0. In 27, what we're looking at is the difference. It looks like we got something squared and something squared, but 45, I don't know the square root of that one. That's not a whole number, and neither is 20. However, 45 and 20 both have something in common, right? There's a 5. The greatest common factor here is a 5. Let's take a 5 out, and when we do that, 45 divided by 5, there's a 9a squared, and then this negative 20 divided by that 5, that's going to give us minus 4b squared, and now we've got the difference of two squares, right? 3a, 2b. So let's factor this one. Now bring the 5 down, don't forget that. Write our two parentheses and put in the conjugates. 3a, 3a, 2b, 2b, 1 will be plus, 1 will be minus, and there is our complete factored form. Now this binomial is not the difference of two squares, right? It's the sum of two squares, 3x and 8. So it's the sum of two squares. There's no pattern for this, so we're going to claim that this is prime. 31 gives us 4 minus v squared, perfect square, right? 2. V squared, square is perfect square, v. So let's write our two sets of parentheses and put in our conjugates. So we're going to get a 2 and a 2, a v and a v. One will be plus, one will be minus. This one looks just a little bit different because in this time we got the constant first and the variable second. Usually when we looked at these before, it's just the other way around, right? Like up here. Variable first, constant second. Variable first, constant second. Now, 25 minus 16b squared is number 33. Perfect square minus perfect square. Difference of two squares. We've got the constant first this time, so it might look a little bit different, but this is going to give us unsquare 5 and 5, 4b, 4b, 1's plus, 1 minus. Now, just for fun here, how about if I just do it differently this time? Instead of plus and minus, I'll make it minus plus. Same result in the end when you multiply it out, right? 5 times 5 is a 25. Positive 20b minus 20b is 0. That's gone. And then negative 4b plus 4b, negative 16b squared. And now in number 39, we have the difference of two squares again. W to the fourth minus 9. So let's write our two parentheses. Unsquare, so what do you square to get w to the fourth? W squared and w squared. And then a 3 and a 3 will make 1 plus and 1 minus. Now, these are not the differences of two squares. First of all, this is a sum. This is a difference, but the 3 can't take the square root of that and get a whole number. So we've got that one completely factored. And you know, while we're at it here, let's look at this. W to the fourth. Now we can write that as this, w squared squared. So if I unsquare w to the fourth, I get w squared. And in fact, if we do this, if we take x and to any power and square it, right, you multiply those exponents, we're going to get x to the 2n. Now 2n, that's an even number. So whenever you look at a variable and you see its power is an even number, you can unsquare that just by taking half of that exponent. So just imagine we had something like this. Suppose you had y to the 10th. Well, divide it by 2, right? This is a 10, that's even. Divide it by 2, we'll get 5. So we'll get y to the 5th squared. So if I had something like this one here, say we had y to the 10th minus 25, I could write that as y to the 5th, 5 and 5, 1's plus, 1's minus. So whenever I have this even exponent up here, even exponent, I can get the square just by cutting it in half. Now on this w to the 4th minus 81, this is problem number 41, I see I have an even exponent here, so I know that's going to be a perfect square, right? I can get this square by taking half of this. 81 square root is 9, so I know I can do this one. So here's our parentheses. How about if we write w squared, a 9 and a 9, make 1 plus and 1 minus. Now look what we've got here. This is the sum of two squares. That does not factor anymore. That part is prime. But this one over here, I've got the difference of two squares. So this one here, we can factor again. And in fact, here's what we're going to get. Let's bring that w squared plus 9 down. Don't forget that one. And then what we're going to have is let's factor this w squared minus 9. So how about w, 3 and 3, make 1 plus, 1 minus, and there is our complete factored form. Now in problem 43, this one's a little bit silly because these numbers are so big. But first of all, I do notice that I've got a perfect square here, right? This exponent is even, so if I unsquare it, I'll get v squared. But 4096, this turns out to be 64 times 64. How do I know that? Because on my calculator, I put in the square root of 4096, and it came back as 64. So what I'm going to write here is, I'll get a v squared and a v squared. I'll get a 64 and a 64, 1 plus, 1 minus. And just like that last problem, 41, this one right here is the sum of two squares. That's prime. We can't go any further. But this one over here, difference of a square and a square. So we can factor that one some more. So we're going to get v squared plus 64. I have to squeeze it in down here. And then we'll get a v and a v, an 8 and an 8, 1 plus, 1 minus. Looks a bit funny here, but I had to squeeze it in. There it is.